This is Chapter 4, Differential Relations for Fluid Flow, Part 4. In this video, I'm going to derive the differential form of the conservation of linear momentum for fluids. We're going to consider a differential fluid element, and then we're going to examine all the types of forces on that element. That includes viscous forces, pressure forces, and gravity. And then we'll look at applying F equals ma on that differential element. And that'll lead to the famous, or some people consider infamous, Navier-Stokes equations, with the assumption, of course, that the fluid is Newtonian. I should mention that this is really just an overview, and a full detailed derivation of the Navier-Stokes equations is really beyond the scope of an undergraduate course. It's more of a graduate topic. This should give you a good feeling for where the Navier-Stokes equations come from. Then I'll end with an example where you get to work with the Navier-Stokes equations. And so given a velocity field v of x, y, z, and t, you're going to be able to show whether that velocity field satisfies conservation of momentum. So in other words, whether or not it satisfies the Navier-Stokes equations. So we're going to start this discussion by talking about conservation of linear momentum. This is Newton's second law. And so what we're going to do is consider a differential fluid element shown over on the right, dx, dy, dz. And it has mass, dm, of rho dv, right? So mass per unit volume times the incremental volume, and the volume of that little cube is dx, dy, dz. Now we apply Newton's second law to this little differential mass. So sum of the forces, which we're going to talk about in the coming slides, equals dm times the acceleration. And of course, I've bolded the F and the A because this is in vector notation. And so I've made the substitution in here for dm. And now for this acceleration vector A, in the previous video, we spent a good deal of time talking about fluid accelerations and how the total acceleration, or the substantive derivative of velocity, is actually two components, right? There's a local component, local acceleration, dv dt, and then this convective component. And so now what we're going to do is make the substitution for A in here, right? So A goes in there. And that's what I've done down at the bottom here. So we've got sum of the forces equals mass times acceleration. So I've made the substitution in here for dv dt. Remember, that's the total derivative. Some books use this capital D, dv dt, to remind you that it's not an ordinary derivative, that it's a substantive derivative. And so I've called this equation 1. This is the equation we're going to come to in the end once we've figured out all the forces that are acting on this control volume. Then we will set it equal to mass times acceleration. So next we'll discuss the forces on the differential fluid element. There are two main classes or types of forces that act on the fluid. These are body forces and surface forces. We're going to handle these individually in the next couple slides. We'll start with body forces. Body forces are uniformly distributed throughout the fluid element. And for the purpose of this course, we're only going to worry about gravity. Gravity is, of course, the weight of that fluid element. It acts uniformly throughout that fluid element. There are other possibilities. For example, if this fluid was magnetic, if it was metallic, for example, or ferrous, and there was a magnetic field, there could be a magnetic force. And in fact, there's a whole field of fluid dynamics called MHD, magnetohydrodynamics, where fluids get pumped using magnets rather than impellers. But that's a pretty exotic application. And for the purpose of this course, we will only have gravity as a body force. So we can define the gravity vector G, bolded here. It has components in the x, y, and z directions, so gx, gy, gz. And so the gravity force on the fluid element is just the weight of this fluid element. So rho times g times the differential volume. That's just the weight of that fluid element. And now it's really your choice to decide which way you orient the axes in an analysis. Often the y-axis is upwards, as I've drawn here. And if that's the case, then g acts downwards in the negative y direction. And so we get there's no component of g in the x direction. In the y direction, g is equal to minus g, the actual gravitational acceleration, so 9.81 meters per second squared, or 32.17 feet per second squared. And then there's no component in the z direction. That's when, of course, you have the axis orientation that's shown in the diagram here. So now we move on to surface forces. We're going to consider the stresses, so the forces per unit area on the fluid element. And there's two sources of these surface forces. There's viscous shear stress and pressure. Now over on the right, I've taken this image from your book. It shows the 9 stresses that exist on the differential volume, and these are surface stresses. The outward pointing stresses here are normal stresses, and the stresses that are on the surface tangential to the surface are shear stresses, such as this one here. And it turns out that the 9 components of stress can be expressed as shown down below, and I've just taken this from your book. These are the stresses in the x direction, these are the stresses in the y direction, and these are the stresses in the z direction. Now, notice the nomenclature here. Sigma, well, let's pick this one, sigma x, y. That's the stress on the x face in the y direction. So the nomenclature here, sigma ij, is the stress in the j direction on the face normal to the I-axis. So you'll notice that on this face here, this is the face that's normal to the x-axis. So you'll notice the first subscript in all these stresses is x here, because that's telling you that it's acting on that face that's normal to the x-axis. And then the second subscript tells you the direction of the stress. So y, you can see it acts in the y direction for this one, acts in the z direction for this one, and acts in the x direction for this one. So we end up with 9 stresses. These normal stresses here have pressure plus a viscous stress. It's beyond the scope of the course really to go into explaining these viscous stresses, but the pressure you can understand. Pressure acts, of course, inward on the face, and that's why the negative sign is there. So on each face we have pressure acting inwards, and so you'll notice that pressure appears on the diagonal here. So we have pressure plus these viscous stresses on the faces. So now we've defined the stresses on each face, and we have 9 components of stress. We can look at determining the net surface forces in each of the directions. And here I've written down the net surface force in just the x direction, and the figure over here on the right that's taken from your book only considers stresses in the x and negative x directions. So for example, if we consider the normal stress on the x face, it's stress sigma xx times the area. dy dz is the area of this face. And then at x plus dx, so just a little bit farther along at dx, we can figure out the normal stress here by using a simple Taylor series expansion that we discussed before. It's a common approach. It's sigma xx plus di by dx dx dx, and then times the area again. This is area dA. Now there's 3 sources of stress or force in the x direction. There's the normal stress that I just discussed, and there's 2 tangential stresses, 2 viscous shear stresses. one on the y face and one on the z face. So let's consider the y face here. So now we're considering the face that's normal to the y-axis. And so on this face we have a shear stress sigma yx times dA. Now this dA is dx times dz. It's actually the area of that face. And then we do a simple Taylor series again at y plus dy. So it's sigma on the y face in the x direction. That's a tau. That's actually a shear stress. Plus di by dy of sigma yx dy, and then times the area. We also have a viscous shear stress on the surface on the z face in the x direction. That's this one here and this one here. And it's the same thing. Sigma on the z face, so the face that's normal to the z-axis, in the x direction times the area dx dy. Now it's getting very complicated here, so I don't want to cross-hash it, but that's the area of this front face here and the back face. And then again, a Taylor series to get this the shear stress here. It's sigma zx di by di sigma zx dz, and then times the face area dx times dy. Now you'll notice that when you're looking for the net force in the x direction, this shear stress cancels with this, right? And this cancels with, make sure I get it right, with that one, and this one cancels with that one. So you're only left with these sort of Taylor series expansion terms. And so you'll see over here that the net force in the x direction is just di by di sigma xx dx dx times the area dy dz, di by di sigma on the y face in the x direction dy times the differential distance dy times the area, di by di stress in the on the z face in the x direction. So these are all in the x direction. You can see by the second subscript, differentiated with respect to z times dz times dx dy. Now you'll notice each one of these terms is multiplied by dx dy dz, so we can bring them out, and we end up with this expression for the net force in the x direction. These are surface forces. We also have body forces as well. So similarly, the surface forces in the other directions, in the y and z directions, can be figured out in just the same way. And I've written them down. You can quickly have a look at them. You'll notice there's three components in both of them, just like in the x direction. So we have sigma on the x face in the y direction, sigma on the y face in the y direction, on the z face in the y direction. So that makes sense. In the z direction, we have the stress on the x face in the z direction, the stress on the y face in the z direction, and the stress on the z face in the z direction. So these are all in the z direction, and these are all in the y direction. Now these stresses, it turns out, are related to the velocity field. And for a Newtonian fluid, the relationship between the fluid stress and the velocity gradient is given by these equations. It's beyond the scope of this course for me to go into details on the discussions of that. That's more of a graduate level topic. But it's important to realize that those stresses are related to the velocity gradients. We're dealing with a Newtonian fluid. So remember what a Newtonian fluid is. It's a fluid where the shear stress is linearly related to the velocity gradient, or the rate of deformation of the fluid element. So these are the drag forces on the fluid caused by fluid viscosity. They're the sources of fluid friction. So now we have all the forces. We can apply our equation 1 from, I think, the second slide, F equals ma, where we have our local acceleration and our convective acceleration, and rho dx dy dz is our mass. As we've just discussed, the sum of the forces has three types of forces: pressure forces, viscous forces, and the gravity force, which is a body force. So we apply the forces that we just derived to this equation, and we do it in a vector sense. We do it in the x and the y and the z direction. I've done this in a graduate course. It takes several pages, and the result is the famous Navier-Stokes equations. So these are the Navier-Stokes equations for a Newtonian fluid with constant properties. So we're assuming density is a constant and dynamic viscosity is a constant. So density equals a constant means that these equations are the incompressible constant property Navier-Stokes equations. And in Cartesian coordinates, we end up with three equations. We have conservation of momentum in the x, y, and z directions. And you'll notice we have the acceleration. This is mass times acceleration, and on this side we have forces. And in the next slide, I'll talk about the meaning of the terms in more detail. So as I mentioned in the introductory video for Chapter 4, these are the equations that are solved in computational fluid dynamics codes for fluid flow. There are some exact analytical solutions, and we'll be talking about a couple of those in the next video. But for now, let's investigate the meaning of the terms a little bit more so that you understand the Navier-Stokes equations. As I mentioned, these equations represent conservation of momentum in the three coordinate directions. They are F equals ma on a per unit volume basis. So I've written here just the x equation. So let's just look at the x equation, so conservation of x momentum. So what we have here is density, of course, that's mass per unit volume. And then the next term here, you can see du dt has units of acceleration, and that's the local acceleration, and then u du dx, v du dy, w du dz are the convective acceleration terms. So over here we have mass times acceleration per unit volume, of course, because of the density. And then on the other side of the equation, we have the pressure gradient force. So this is pressure per unit volume, pressure force per unit volume. This is you can see the viscosity here, dynamic viscosity. So this is the viscous drag force per unit volume. And then we have the gravity force, and that's the gravity force per unit volume. So if we look at the units now, of course, density has units of kilograms per cubic meter. Acceleration is meter per second squared. So you can see this is kilogram meter per second squared per unit volume. And on this side we have newtons per unit volume. You can imagine pressure is force per area, so force per meter squared, and then we have another x on the bottom, so we have newtons per cubic meter. And this equation is dimensionally homogeneous, so you can easily show that all the terms have units of newton per cubic meter. And so we have, if you cross out the cubic meters here, we have F equals ma, right? Newton is a kilogram meter per second squared, so everything is consistent. And so the acceleration terms are acceleration per unit volume, and the force terms are the pressure, viscous, and gravity force terms, all on a per unit volume basis. That should give you some idea of the meaning of this quite complicated partial differential equation. I mentioned also that the reason these equations are so hard to solve is because of these nonlinear terms. It's the v du dy. You've got two unknowns multiplied together here, and it's these convective terms that make the Navier-Stokes equations nonlinear and quite difficult to obtain exact solutions to. And you'll see when we do the exact solutions in the next video that we managed to get rid of those nonlinear terms. As I discussed in a previous video, when we did conservation of mass, sometimes it's desirable to work in cylindrical coordinates. This is particularly the case when your geometry is cylindrical, like when you're considering flow in a round pipe. And so you can do that same conservation of momentum analysis in cylindrical coordinates, and that's not done in your book, but the result is given in Appendix D of your book, and I've reproduced them here. we have three coordinates, right? R, theta, and z, and so you end up with a conservation of momentum equation in the R, theta, and z directions. And they look quite complicated, but they have exactly the same terms. They have an acceleration term, a viscous term, a pressure term, and a gravity term. The last thing I'd like to talk about before I do the example is inviscid flows. Recall that flows with no viscosity are called inviscid flows. Now, all real fluids have viscosity, so this is really an idealization. And what I've shown here in the diagram, which is actually from chapter 8, is flow over, say, two airfoil-shaped objects. And you may recall from the discussion of Bernoulli's equation that far away from solid surfaces, real flows can be approximated as inviscid. The flow away from the surface behaves as if the dynamic viscosity was zero. Now, near the surface, what happens, of course, is we have the no-slip condition. And very close to the surface, the action of viscosity slows the fluid down, and viscous effects cannot be neglected in this region. So you end up with a viscous boundary layer near the surface of fluid that slowed down, and in that area you cannot apply or you cannot approximate the flow as being inviscid. But well away from the surface here, we have an external inviscid flow, and between the two airfoils here, we have an inviscid internal core. So the flow in this region would behave very much like the flow had no viscosity. And so if you want to solve the flow in that region, one way to do it is to take the Navier-Stokes equations and set the dynamic viscosity equal to zero, which is the same, of course, as setting the shear stress on a fluid element equal to zero. And you can very easily show that the Navier-Stokes equations simplify to this equation here. This equation is called Euler's equation. So what you're left with here is rho dv dt. Now recall that this term here is the substantive derivative. And then you've got the pressure gradient and the body force due to gravity. Here I've rewritten Euler's equation again. Now, when we studied Bernoulli's equation, we actually considered a fluid element and did F equals ma, Newton's second law along a streamline. An alternate way to derive Bernoulli's equation is to integrate Euler's equation along a streamline, and you end up with the same result, the famous Bernoulli's equation. I thought I'd just end with a little bit of history here. Euler's equation was derived in the mid-18th century before the equations for viscous flow, the Navier-Stokes equations, were known. And you've run across Euler, 18th century Swiss engineer, physicist, and mathematician before. When you studied classical beam theory, slender beam theory, that's often referred to as Euler-Bernoulli beam theory. And if you looked at the buckling load on a slender beam, he was the first to sort of come up with a solution to that called the Euler bucking load. And of course, you've seen his work in mathematics, the Euler formula for e to the ix. So I'll end with an example that demonstrates how to work with the Navier-Stokes equations. So the example says, consider an incompressible flow of a Newtonian fluid with the velocity field given by this vector expression. So we have minus 2xy in the I direction, y squared minus x squared in the j direction, and 0 in the k direction. And you're told to neglect gravitational effects, so basically we're going to assume G is 0. And with that assumption, you're asked, does this velocity field satisfy conservation of momentum? So in other words, does it obey the Navier-Stokes equations? So the solution starts with looking at the nature of the flow. It's, of course, you're told it's steady, and you can see it's steady because there's no time in either any of the velocity components. You can also see that that you only have u and v components, so it's two-dimensional, so you only need to consider conservation of momentum in the x and y directions. We have no velocity in the z direction, so we don't need to consider conservation of momentum in the z. So I start by writing down the x momentum equation. This is the Navier-Stokes equation for the x direction. And notice too, I've written down here that I've extracted the components, that this is u, this is v, and of course w0. So u equals minus 2xy, v, the velocity in the y direction, is y squared minus x squared, and we have no velocity in the w direction. So you can see here the Navier-Stokes x equation. We have the acceleration terms, pressure, viscous forces, and gravity. Now you're told that the flow is steady, so we can cross out the local acceleration term. We also are told through the velocity vector that w0, so this term here goes to 0. And you're told in the problem statement to neglect gravity, so we can cross out the gravity term. So now we can look at evaluating the remaining terms. So making the substitutions here, I've got rho, and then 0 for the local acceleration. Now here we have u du dx, so u is minus 2xy, that's correct. And then the derivative of u with respect to x is going to give you minus 2y, so that's correct. And then v is y squared minus x squared, that's correct. And then du dy is going to give you minus 2x, so yes, I agree with that. And then this convective acceleration term in the z direction is 0 because we have w0. So I agree with that's 0. Then we have the pressure gradient, and then the viscous terms. We want to take the second derivative of the u component with respect to x. Well, if we take the derivative once with respect to x, we're going to get minus 2y, and then you take the derivative again with respect to x, you're going to get 0. And the same thing if you take the derivative with respect to y twice, we don't have y squared, so that's going to go to 0, and there's no z in the u component, so when you differentiate it even once, you're going to get 0, and we're told to neglect the gravity term. So I just checked, I agree with that expression. Now what I've done is done a little simplification. I've collected some terms. I think I've done it correctly. You can check my algebra. It's very straightforward. So that's our pressure gradient in the x direction. Now what I'm going to do is consider the y momentum equation. So the next slide is exactly the same, but I've written the y momentum. So you'll notice that v is in the momentum equation here. And we have the pressure gradient in the y direction and the viscous stresses associated with the y momentum equation. I've crossed out again the local acceleration term because we're told it's steady, we know w0, and we have no gravity. So we just have these terms remaining. We do the same thing. We make the substitution. So we have rho times 0, then u, which is minus 2xy, and then now dv dx. So we have to differentiate this with respect to x, and that's going to give you minus 2x. So I agree there. And then v, and then dv dy. So that's going to give you 2y here, right? I agree with that. And then w0, so that's term 0. That term is 0. We have dp dy. Now the viscous terms this time, we're differentiating v with respect to x twice. So a first derivative is going to give you minus 2x, and then a second derivative is going to give you minus 2. And now here we're differentiating v with respect to y twice. First derivative is going to give you 2y, and then the second derivative is going to leave just 2. And then there's no z in v, so differentiating with respect to z gives you 0, and we're neglecting gravity. Now once again, I've done a little bit of collecting of terms. I'm not going to spend time on this. You can check my algebra. Now in the next slide, what I've done is I've reproduced dp dx and dp dy are two results. So we had dp dx, and now we have dp dy, and the top line of the next slide, I've just reproduced what we've shown so far, dp dx and dp dy. Now, you got to remember that, and this is not well explained in the book, the pressure field P of x of y is of course a single function. It's a continuous function, a single function, and so to determine if those gradients that we just determined in the x and y directions are compatible, we need to evaluate the mixed derivative. In other words, take the derivative with respect to x and y of the pressure field. And if those two derivatives are the same, mixed derivatives are the same, then we have a compatible pressure distribution. In other words, we have a single function for pressure. So what I've done here, for a single function, these two mixed derivatives must be equal. And what I've done is I've taken the derivative in the y direction of the x gradient. So this x gradient gets substituted into there. So I've taken the derivative of this in the y direction. And of course, so that's di by dy of minus 2 rho xy squared x cubed. Of course, we treat that as a constant. So that's going to just become, in the y, the 2 is going to come down and you get minus 4 rho xy. Now I've repeated this. I'm taking the derivative of this pressure gradient in the x direction. So that substitution, that goes into there. So di by dx of minus 2 rho yx squared plus y cubed. And if we take this derivative here, this is a constant, so you're going to have minus 4 again, rho xy. And these are equal. So we come to the conclusion that we have a compatible pressure distribution, and thus the velocity vector field satisfies the Navier-Stokes equations. And that completes that example. For the last slide here, I've just shown an interesting little animation that shows vortex shedding off of a cylinder in crossflow at a Reynolds number of about 150. Vortex shedding starts around a Reynolds number of around 60, and you get these alternating vortices coming off the cylinder. It's a really cool emergent property of the Navier-Stokes equations. Results largely from the nonlinearity, and you can see the beautiful agreement between CFD prediction and some actual experimental flow visualization. And that completes this video.